Then we'll go with some questions here. All right. Who would like to begin? Questions from homeworks. Who would like to begin? Giselle, I'm counting on you to get us started here.
I got it.
Okay.
We'll start with 45, maybe.
Sure. We can do 45. And then 27. Okay. So when I look at this, I see, oh dear, there's like a whole bunch of chain rules in here, like 3 or 4 or 5 of them. I can't tell maybe right away by just glancing at it, but there's going to be a whole heap of them, right? I would not try to do this by doing like f of x and g of x and then h of x and k. Like you're just going to run through like the entire alphabet pretty quick. I'm just going to think about this as like derivative of the outside times derivative of the inside over and over and over again. So if I look at this initially, what is my outside function to start with? Cosine x, right? The derivative of cosine is negative sine. And then like all of the innards are all going to stay the same. And then we have times the derivative of the innards. Okay. So that stuff is going to stay. Now let's do the next derivative. So what is the outer function for the derivative of the square root sine of tan of pi x? It's the square root, right? And Katie, you're right. Let's think about that as like a power rule with an exponent of 1/2. So when I do my power rule, I do that, and the innards stay the same. And then I have times the derivative of the innards. So again, that part's going to come down, that part's going to come down. And now I need to do the derivative of sine of tan of pi x. The outer function here is sine x. The derivative of sine is cosine of the innards times the derivative of the innards again, comes down, comes down, comes down. And then to do the derivative of tan pi x, the outer function is tangent, or tan x. The derivative of that is secant squared times the derivative of the innards. And now I'm just going to write out my final answer here. And then the derivative of pi x is just pi, right? Just like that part. I have that part. I have that part. I have that part. And I have like that part. Does that feel okay, Giselle?
Yeah, I was trying to do it with the f of x and then the g of x.
It just gets to be a lot, right?
Yeah, I was lost.
I think that just taking one layer at a time, when you have like, okay, I have like a bunch of functions like composed inside of each other, it just becomes a lot to like write down, to do like f of x is this, and g of x is this, and k of x is this, and h, and just like I'm just gonna do one layer at a time, working from the outside in, and just keep peeling those layers back until there's nothing left to do, until all the chain rules are finished, and then I'm stopping. And again, I don't think really there's even much simplification you could do here. And you could write it as a fraction with the negative exponent in there or something, but not a lot to do there. Does that feel okay? What's next? 41. Okay. 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 Very similar problem. So again, I look at this and it's like a bunch of chain rules. This is what I see. What is the outermost function? That's not a function that we can differentiate, though. It's not sine x. It's x squared. Very good, Katie. So remember that sine squared means the same thing as like sine of x quantity squared. Like that, right? Everybody's okay there? But that's what sine squared x means, is just sine of x quantity squared. So the outermost function is x squared, as Katie stated. So when I do that, I just do a power rule, right? And then the inside stays the same. And then I have times the derivative of the insides. So that part just stays the same. When I look at the derivative sine of e to the sine squared t, sure. The outermost function there is sine x, and the derivative of sine is cosine. When I say those and I pause, feel free to just like shout it out if you know the answer. It's just good practice. And then times the derivative of the insides. So again, that stuff just comes down. The outermost function of e to the sine squared t is e to the x. So the derivative of e to the x is just e to the x, so that part just stays the same, times the derivative of sine squared t. The outermost function on sine squared t is x squared. So that's 2 times something to the first, and that first, or that something is sine t, and then times the derivative of sine. Oh my goodness, guys. All right, that's fine. So when I've written d dx each of these times, what do I really mean here, though? D dt. Not like the wrestling move. Wrestling fans. Why should it be a t there? Yeah, because the variable is in the problem is t. Yeah, good. And so now I have like really everything I need. So is that starting to feel a little bit more manageable when we kind of just like sometimes like discarding the keep it organized once you have the idea of the rule?
Yeah, it's a lot more organized than what I was doing.
Just makes life easier. Like, again, just try and do one chain at a time. Oftentimes it gets like kind of overwhelming when we have like, you know, like 5 or, you know, 4 or 5 compositions together. Like that's a lot to kind of keep track of. Like, so this, you know, f of x of f of g of x, and then g of x is h of k of x, and then, you know, k of x is, you know, j of l of x, and then l of x is, you know, like it just, you run through a lot of letters and it gets to be a lot. This I feel like is just like in a way easier by writing less, or clear, easier to follow, because it just like do the outside derivative, inside stays the same, derivative the inside, and then, you know, just keep peeling away those layers. But this I think is, again, like now that you've seen me do it, like this is a reasonable still test question. It's a hard test question, but like this is still reasonable.
Yeah.
Because it's like, well, okay, like I can see that I can do it in a couple lines on my paper. It's not like a whole sheet.
Right.
Maybe like I spent trying to do it the first time. And that's, I think, plenty adequate in terms of work shown, right? As a reader, you can follow that. I hope, right? Yeah. Let's keep going. You guys got some more? I know this can be a difficult section. I think this is the one kind of like make or break section for this test. Like if you can't do the chain rule, especially in combination with the other rules, it's going to be a long chapter. So this is the one that like, this is the homework assignment that I really care the most about. Casey? Sure. This is the place where like we're really kind of doing the most derivative calculus or symbolic derivative calculus of the whole semester is right happening now. All right, so we have y of square root 1 plus 2e to the 3x. So again, what's the outermost function here?
Square root of x.
Yeah, the square root of x, or I'm going to think about really x to the 1/2. So when I do the derivative of the outside, that's just a power rule. And then the inner stays the same. And I have times the derivative of the inner. So that part will stay the same. Now to do the derivative of 1 plus 2e to the 3x, well, the derivative of 1 is 0. and I can pull the 2 out front because it's just a constant. But the derivative of 3e to the x requires a chain rule. The outer function for e to the 3x is e to the x. The derivative of e to the x is just e to the x. That stays e to the 3x. Oops, not there though. And then it's times the derivative of the insides, which is 3x. So there's that. And I think we end up with then like 3e to the 3x over square root 1 plus 2e to the 3x. It's probably what the answer in the back looks like. Does that feel okay, Casey?
Yeah.
I know it looks like looks so easy. And it's not, especially the first time you're doing it. Like, these should be challenging, and they should have felt not trivial to do. Is that felt okay though?
Yeah. I think I actually it might have been, I don't even think, it might have been 19 that I came up with. I don't.
Oh.
Yeah. No, sorry.
That's okay. Take a quick look and let me know.
Yeah.
We can certainly do 19 if that's.
Either 19 or 23, so I think it must have been.
You think it must have been 19?
Yeah.
Okay. We can do
Sorry.
19. No need to apologize. You could have stopped me as soon as you saw the problem and like, oh, that's not the one I thought.
No, that's okay.
It's okay. You don't have to. Nobody has to be right all the time. I'm certainly not. This look
Yeah.
more the problem?
Yeah.
Okay. So when I look at this, I don't see a chain rule to do right away. When I take the derivative of this, the first thing I'm encountering is that I have the product of two functions. So like this is my f and that's like my g. Now when it's time to do the derivative of f and the derivative of g, when I'm doing my product rule, then I need to do the chain, right? So this will be a product, and inside of the product is two chains. So I'll have the derivative of, well, I'll just do f times the derivative of g. And the g derivative, or g doing the derivative of g requires a chain rule, right? The outer function there is x cubed. And then the inside will stay the same. And then times the derivative of the insides. And then I have, again, this is f, it's g prime. Then we'll have g. And then we need the derivative of f, which again requires a chain rule. The outer function is x to the 2/3. The inside stays the same. And then times the derivative of the insides. And that should be a t there. Because this is now f prime. Feels good so far? Okay. Let's put the 3 over there, I guess. To the derivative of 2t squared minus 1, just going to be 4t minus 0. And the derivative of t plus 1 is just going to be 1. plus 0. So there's an answer. Calculus is done. That's not what the answer in the back of the book would look like, but that's okay for us. If I wanted to do that, what would I do here?
Factor out the 2t squared minus 1 to the squared.
Yeah, I would do that. And then I would do, I'd have this to the first. Sorry, hold on a second. Let's do this one at a time. This is going to get too overwhelming for everybody if I try to do this all at the same time. Come on, Kulik. Don't go crazy here. So far, so good?
Yeah.
And then maybe I'd factor out a t plus 1 to the negative 3, or negative 1/3, excuse me. So when I do that, t plus 1 to the positive 2/3 just becomes t plus 1 to the first. Right, because when I factor it out, it's like dividing with the negative exponent. I end up adding the exponents. And then I can just FOIL things out in here. And combine some like terms. What's that? 36 plus 4, or plus 4 is 40. Maybe that's the answer in the back, would be my guess.
I think so. I thought it was like 12 plus 18 minus, I might be wrong.
Yeah. I'm always interested to see what they simplify some of this stuff down to, if they're like more clever than I can be.
I just got more stuck with like the back part.
Right, yeah. So again,
When
when
they got 2 over 3 times t plus 1, so that's negative 1/3 times 2t squared minus 1 squared. Or, yeah, I'm not gonna say this right.
So yeah, all they did is they took a 2/3 out of this then and put it in the front. Right, so they factored a 2/3 from here. So if they did that, let's see, 12 divided by 2/3 is like 18. And then that would be 20. And then that would be 1.
Okay.
Is that?
Yeah.
Okay.
It was 20 squared plus 18.
What's going on? Oh, interesting. What did I do wrong then? Okay. Okay, that was all. I think they might have transposed some numbers there. Yeah, Yeah, they sure as heck did. Oh no, wait a minute. Oh, look at what I did. No. Look at this. Look at this. That's supposed to be 2t squared. So, I don't know, something, those aren't right. But that should be 18 and 20 then. Oh, they were right.
Okay.
I made a mistake, but shame on all of you guys for not catching that I dropped an exponent there. That's okay.
Thank you.
Of course. Giselle.
I just have a question. It's on number 29. But what's the what's it called, base function?
Outer.
Or the outer function of t sine 2t?
There isn't one. It's a product rule.
Okay, can you just do number 29?
Yeah, of course. Okay, so the outer function is of e to the t sine 2t. It's just e to the x. So derivative of the outside is just the same thing, times the derivative of the inside. So if I look here, there is no outer function to t sine 2t. What it is the product of one function, t, with another function, sine of 2t. So to do that derivative, I need to do a product rule. Does that feel okay there?
Yeah.
Okay. Now, when I differentiate g, when I'm doing f times g prime, to do the derivative of g requires a chain rule. The outer function is sine of x, whose derivative is cosine. And then the derivative of the inner function is 2t. And then I'll have g times the derivative of t, which is just 1. The derivative of 2t is just 2. And that's probably what they left it as. Is that, you feel good about why you had to do the product rule there first?
Mm-hmm.
Okay. Nolan.
You do over 17.
Sure. So when I look at this, this looks to me quite similar to what we saw in 19, right?
Yeah.
So again, I think it's just going to be a product rule
Chain.
with chain rules inside. Exactly right.
I think I got the calculus. Just simplified that.
Okay. So let's then grind through this real quick. Okay. And then when we do the calculus, this is 2x plus 1, right? And then this is just 2. And let's see if we can get their answer that we simplified to. So I'm going to take out greatest common factor of 2x minus 3 to the third, and then x squared plus x plus 1 to the fourth. So in the first piece, I have that 5 times 2x plus 1, and then I have a 2x minus 3. And in the second piece, I have that 8, and I have an x squared plus x plus 1. Does that all look okay? So FOIL that out, I'm going to have 4x squared times 5 is 20. And then I'll have a negative 6x plus a 2x, that's a negative 4x, times 20, or times 5 is 20. And then a negative 3 times 5 is negative 15. Distribute that stuff through. So that's going to give me 28x squared minus 12x minus 7. I wonder if that's
that's what they got.
what they got.
Yeah, for some reason when I factored out the x squared plus x plus 1 before, I like didn't take it all the way out on one side, so I was messing up my folder.
Yeah. Yeah, it's nice that the piece with the 2x plus 1 didn't have any x squared plus x plus 1, so you didn't have like a triple FOIL, which stinks. But that ought to do us. Okay, that's good. And again, just for the record, like if it's a free response question, you're fine stopping when the calculus is done, right? You'd be okay at that start spot when we finished all the calculus to stop if it's a free response question, either on my test or on the AP exam. The multiple choice questions, though, if they ask you to do this problem, none of the answers are going to look like that. They're going to look like the simplified version. So you do like need to at least go, okay, this and this. Like, if I don't go simplify all the way to get there, which you probably don't want to do more often than not, I would first check by saying, okay, like, here's my answer. Could it be A? No, the exponents are wrong. Could it be B? No, the inside stuff is wrong. Could it be C? Well, maybe. Could it be D? No, that can't be that. And just like see if you can eliminate down to like not have to do all the simplifying. Sometimes you might, because you just don't see it. But that's where they, on the AP exam at least, where they will get you with the simplification. Does that feel okay? You understand what I'm saying? Which again, I think is important, especially on the homework, that you try to simplify to what the back of the book gets. Even if you don't get it right, it's good practice. It helps you like find things that you're making mistakes with, or you come in and talk about it the next day or this next day in class, and it's like, oh yeah, that's a really clever way of kind of like doing some simplifying or some factoring, or like, you know, moving terms around to get things to cancel out or whatever. Or it's like, okay, that's a cool trick. I'm going to hang on to that because that makes, when this kind of problem shows up, like that's helpful. You know, like the factoring that we did, you know, to pull these things out. Like that's a nice observation of like, oh yeah, I could factor like that, couldn't I? certainly makes much easier getting to the final answer if you catch those sorts of things. Katie, 25? Certainly. Oh my God, I'm so far zoomed out. Okay. So I look at this and I see definitely a chain rule because the exponent isn't just an x. So the outermost function is 5 to the x, right? What's the derivative of 5 to the x? It's 5 to the x times the natural log of 5, right? The new derivative rule that we got in addition to the chain rule was this one. And remember, this is just a generalization of our rule for e to the x, because what's the natural log of e? 1. So it just becomes e to the x times 1, or just e to the x. So this is just a generalization of that rule that we've seen before. So here, the derivative of the outside is that and the derivative of the inside is just the derivative of negative 1 over x. Now, what's going to be the easiest? How do you want to do the derivative of negative 1 over x? Oh, I wouldn't. What if I just think about it as negative x to the negative 1?
How did I not think of that?
Would that be much easier than a quotient rule? I think so.
Yeah.
Right? Look for the easy way outs. So I can just do a power rule there and then, do some combining of like terms here or whatever. I don't know I suspect they're going to be fine with the negative exponent because they had a negative exponent before, but I don't know. I mean, if you wanted to, you could write this as like negative natural log of 5 over x squared 5 to the 1 over x or something. I don't know how they have it in the back of the book. Whenever they give you negative exponents in the problem, I can never guess if they're going to simplify with negative exponents in it or without the negative exponents in it. I don't know. But again, if you get to where the calculus is done and this is just like a free response question, you're golden. Like you don't have to do more than that for me. Or the AP, right? If it's a free response question, unless it specifically says like show something, just, like go to the calculus is done and then stop. Don't simplify. Especially if it's a no calculator section. Mistakes happen. Just do the calculus and be done with it. Don't waste your time. We'll probably need all those seconds. Because it's hard stuff that we're doing, right? Who's next? Katie, I'm sorry. You 27? Sure. Your hand was behind Brooke, so I couldn't see it at first. Then you started smiling more oddly. I was like, I think Katie's trying to ask. Okay. So when we look at this one, what does it appear we should do first? I see a quotient rule, right? Because there's not one outer function. Now, if you were like really clever, you could probably work this down into a single chain rule. Or, I guess it would be a chain and a product. That's probably not any better. I'm trying to think. maybe I could get it into a single chain. Yeah, it's not even worth it. The quotient rule would not be difficult to do here. Let's just do that. Sound okay? Okay. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Notice that I didn't bother to write square root squared. I just left both of them off. So that wasn't a typo on my part. It was just like, that's what I did. The derivative of r is just going to be 1. To do the derivative of the square root of r squared plus 1, what do I need to use? A chain rule. So the derivative of the outside should be this. And the derivative of the inside would be 2r, right? Can we see that without me having to write ddr of r squared plus 1? It's okay? Katie, you're good? Okay. So those can cancel. Let's see what kind of clever factoring we can employ. So I think I can do a lot better than this. If I just multiply the top and bottom of this by r squared to the 1/2. When I do that and I multiply to the numerator, I just have r squared plus 1, right? For the first term. When I multiply to that term, I just get an r. Oops. Got it down here about 2. No, just do that. When I multiply it to here, I'm going to think about that to the first, so I'm just going to add the exponents. I think that's probably as good as we can do. Does that feel okay? Ooh, hold on. Look what I did, Katie. I forgot about this r over here. So that's squared, and that's supposed to be a minus sign. Oops-a-daisy. There we go. Does that feel okay? What's up, Case? Yeah. This is the worst one in the homework set.
Oh, okay.
Yeah.
How long did it take second hour to do?
Well, they interrupted me a lot. So it took probably 2 or 3 times as long as it was supposed to. But I didn't put a watch on it. But we were at it for a while. But it was a good one because, like, by the time you're done, it's like you really understood what the heck was going on, because there's a lot of stuff here. So it says, show that the function y equals yada 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 satisfies the differential equation y prime minus 4y prime, or y double prime minus 4y prime plus 13y equals 0. So what I'm going to do is I'm going to calculate using my function first y prime, and then I'm going to calculate y double prime, the second derivative, and then plug all three of those, y double prime, y prime, and y, into that equation and show that it all cancels out to 0. So let's do y prime first. If I look at y, the first thing I need to do if I'm differentiating that is to do the product rule, because I have e to the 2x times stuff, right? So I'm going to have f times the derivative of g. So to do the derivative of a cosine 3x requires a chain rule, right? So the outer function is cosine. A is just like a coefficient, like a 2 or a 7 or whatever. So I'm just ignoring it for now. So that's going to be a times negative sine 3x times the derivative of 3x. And then we'll do the same thing here. So it's going to be b cosine 3x. I guess it should be there. Yeah. Times the derivative of 3x plus, I have a cosine 3x plus b sine 3x. And then to do the derivative of e to the 2x is a chain rule. So derivative of the outside is just e to the 2x. We have times the derivative of 2x. So derivative of 3x is just 3, and the derivative of 2x is just 2. So if I multiply this or factor this out, I'm going to take off the e to the 2x, and then I'm going to have negative 3a sine 3x plus 3b cosine 3x plus 2a cosine 3x plus 2b sine 3x, or I'll probably simplify this down to do the second derivative, because I noticed that like this guy and this guy contain a factor of sine 3x. And the other two remainings contain a factor of cosine 3x. And I like that form to differentiate again because, well, it's just now one product property and then two chain rules, just like the previous one was. Just the coefficients are more annoying looking. I'm going to leave a little bit of space, though, because I think I'm probably going to want to multiply all that out when I plug it back into the differential equation that I highlighted in green. So I'm going to leave a little space for me to multiply that all out. So we'll do it again. So I have e to the 2x, and then I'm going to do, this is like, f and g. So the derivative of g is going to be, again, 2b minus 3a is just like a coefficient. But to do sine 3x requires a chain rule. And again, 3b plus 2a is like a coefficient. But cosine 3x requires a chain rule. And then I'll do the other part of my product property. And then e to the 2x, again, requires a chain rule. So the derivative of 3x is just 3. And derivative of 2x is just 2. So again, I'm going to factor off the e to the 2x. And then I'm going to have a 3. What am I going to do with that? What's the best way to do that? I think I want to distribute that into here. So let's make that 6b minus 9a cosine 3x. We'll do the same thing there. So it's going to be a 9b plus 6a. That's actually, you push the negative through on that too. Yeah, that's probably a good idea. How are we doing so far? It's a lot, I know. And then I'm going to push this 2 through. Yes, thank you. Oops. And now if I look, this guy and this guy are like terms, so I can add their coefficients. So 6b plus 6b is 12b, and negative 9a plus 4a is negative 5a. And doing the same thing with the signs, I'm going to get negative 5b minus 12a. Bracket. So that's my second derivative. All right. Now if I look at the green thing, that's the second derivative. I'm going to multiply this all out. So I'm going to distribute the 2e to the x in, and then the cosine through here. And then I'm going to have minus 4y prime. So I'm going to take my y prime and kind of do the same thing, multiplying by negative 4. I feel like I goofed a negative sign somewhere, but I'm going to hold to the end before I go hunting for it. Maybe it's still okay. We have plus 13y. So again, I'm going to multiply the y out and the 13. Or was that problematic? All right. This, though, was supposed to be a 12. It's 8, 12. Oh, this one was supposed to be the... No, so I did that in the wrong order. Hold on one second. 3b times negative 4 is negative 12b, and then 2a times negative 4 is negative 8a. Okay. All right, let's take a look here. So I have 12b e to the 2x cosine 3x, and then a negative 12. So that gives me 0. I have positive a e to the 2x sine 3x and a negative a e to the 2x sine 3x. So those give me 0. Then I have negative 5a e to the 2x cosine 3x. And, oops, this was supposed to be a cosine here. And a negative 8a e to the 2x cosine 3x. So that's negative 13a e to the 2x cosine 3x, and a positive 13a e to the 2x cosine 3x. So that stuff is 0. And then negative 5, negative 8, that's negative 13, and a positive 13 is 0. So if like I added all this stuff down, I get 0. And that's what I needed to show. Woof!
Thank you.
Yeah, that was a mouthful. Everyone took me much longer during second hour to do this because I got interrupted about 150 times because it was like maybe the second question they asked. So like it was like every 2 seconds it was a question about something or this thing or that thing or whatever, and then there was conversations about how best to simplify things, and like people were getting confused because someone was asking me about like, could you simplify this, and I did it some other way, and they're like, wait, which one? And then they're doing only parts of it, and it's like, oh my goodness, hold on, just like too many questions happening too fast. But it took a long time. You guys were much more patient with what I was doing, and that was much less time than we took second hour. Chanel.
So would you recommend, because I know you talked to this about me this morning, so would you just recommend for simplifying, just like look at it and try to like simplify as much as possible?
Well, this problem was different because the directions were show.
Okay.
So this one, they definitely like, they needed you to get to showing that, like, if I take the second derivative minus 4 times the first derivative plus 13 times the function, you just, everything cancels out and you get 0.
Oh, okay.
So like you had to do some kind of simplifying to where you can combine like terms in an intelligent way. You could have probably, in hindsight, kept everything in like looking like this. And it would have been okay. So if I left that one like that, and I left this one like that, I would have had, like, would combine this thing with negative 4 times that. Oh, that is negative 4 times it already. I don't know, whatever. You would have, like, you could have left it all in that factored form, but I think it would have been a little bit potentially trickier to kind of see the combining of like terms, and it would have been shorter, but like maybe the combining of like terms wouldn't have been as quite as obvious than when I multiplied everything out.
Okay. For the test, like so for 45, I did like a really long method for like, I don't know if you remember, 45 was like the one with the like.
Let's scroll back.
Root pi.
Oh, the first one we started with. Yeah.
Yeah. Would it be bad that it did it in sections like tan pi x?
No, if you arrived at the right answer, that's fine. My caution too is the time part.
Okay.
Right? Like the tests are timed, the AP exam is timed, my tests are timed. They're not infinite time. So like oftentimes it's going to be helpful to practice like, what's the shortest way I can do this?
So you pretty much just took every part individual?
Yeah.
Like,
I just kept doing one chain rule at a time.
okay.
You know, I did the derivative of the outside, and then to do the derivative of the inside required another chain rule. So I did that as a separate step. And then that in derivative of that inside took a chain rule in separate steps. And every time I use the chain rule, it's just like one more step, but I'm not going to like recopy everything the whole way down. Like I'm just going to be like, you know, this stuff just kind of all comes down. You know what I'm saying?
Yeah. So you just kind of took like each portion and then like kind of multiplied it.
And it,
Yeah.
and just
Yeah.
left at the end,
Yeah.
which is like compact, right? It has that going for it because there's not a lot of space chewed up here. It was whatever, like 6 lines of paper or something, which is still a lot of lines, but like not a whole sheet. And much less to like keep track of in a way.
Yeah, because I found that like I was using like A of X, B of X, C of X. I was using like a bunch of like Y.
Yeah, you're doing a lot of letters on a problem like that. Yeah. And here it's just like, you just got to kind of pay attention to where you're at in the problem, but there's no like grinding through a bunch of letters. There's not an extra bunch of notation to hang on to.
Okay.
Sometimes the more chain rules you have at a time, the quicker I am wanting to abandon, like, okay, this is my F and this is my G, you know, like,
Yeah.
because it just like, ugh. You guys want to talk about anything else? I'm happy to do some more if you guys want to do some more. Audrey? 70? Sure. Nobody asked about this last hour. I did all these problems at one point, but it's like I don't do them right before I assign them. Like I did it, you know, I did them like potentially, you know, like over like years ago when I read through the book or whatever and picked the problems that I liked. So it's always kind of an adventure when it's like one this deep that I haven't looked at in a while, but it'll probably be fine. Okay, let g of x equal some stuff and h of x equal some other stuff where a couple of things are true. Find the first derivative of g with respect, or evaluate at 0 in terms of c in the second derivative. Okay, that's fine. So let's start there. So g prime of x is going to be equal to the derivative of e to the cx, which requires a chain rule. So the outer function is e to the x. So the derivative of that is just e to the x times the derivative of the inside. And the derivative of f of x is just f prime of x. So this just becomes c e to the cx plus f prime of x. G double prime of x, well, to take the derivative of c e to the cx, again, requires a chain rule. So the derivative of the outside is just going to be c e to the cx times the derivative of cx plus the second derivative of f. So that's going to be c squared e to the cx plus the second derivative of f. So yes, g prime of 0 is going to be c e to the c times 0 plus f prime of 0. So c times 0 is 0 and e to the 0 is 1. So I just have c. And we're told that f prime of 0 is 5. And the double prime, so do the same thing. So I have c squared plus, and f double prime of 0 is -2. So there's our answers for part A. Does that feel okay what we did there? And then part C says find, or in terms of K, find an equation of the tangent line to the graph of H at the point x equals 0. All right. So first thing I'm going to need if I want the graph of a tangent line is a slope function. So that's going to be the first derivative of H. To do the derivative of H, I'm going to have to first do a product rule. So my f is e to the kx, and then the derivative of f of x is f prime of x. And I'll have f of x times the derivative of e to the kx, which requires a chain rule. So the derivative of the outside is just e to the kx. Derivative of the inside is just going to be k. I'm not going to write d dx of kx if that's okay. So the derivative then at 0 is going to be my slope. So k times 0 is 0, e to the 0 is 1. F prime of 0, we're told, is 5. F of 0, we're told, is 3. E, or k times 0 is 0, e to the 0 is 1 times k. So this slope is 5 plus 3k. So, and the point we're using is going to be 0, 3, right? Because that's my x and y. So I have y minus y1 equals m times x minus x1, or just y equals 5 plus 3kx plus 3. There's my equation for my tangent line. Does that feel okay? Yeah. Again, whenever you see like the K's and the C's and like feels weird, but they're just like treat them like a number, you know, like treat it the same way you would a 2 or a 7 or a 9 or whatever. And the wording, again, like feels like a lot, but basically all I'm saying, okay, g prime, I know how to do that, just taking the derivative and plugging in 0. G double prime of 0, just taking the derivative again and plugging in 0. You know, equation of a tangent line, well, I know how to do that. I just need the derivative evaluated at the x value. You know, like, it's just like a little more abstract because there's some constants floating around in it, but it's okay. It's okay. What do you guys think? Does this feel any clearer after doing some more examples? Happy to burn the whole day just kind of doing some more questions on it. Again, this is, I think, the most important section from this set of sections kind of moving forward. Like if you can't do these derivative rules in combination with one another, life's going to be like, things are going to be a problem kind of going forward. Like this is the kind of the core skill of first semester, is being able to do these derivative rules in combination. You know, do a problem where there's, you know, products inside of chains, inside of quotients, or, you know, like quotients inside of products, inside of chains, and like, or a bunch of chains together, two products together, two quotients together, whatever, like where you have a lot of that stuff kind of all happening at the same time. It's important that we're able to kind of do these effectively, so I don't mind spending some extra time here, because it is maybe the core skill of first semester. And probably, you know, like maybe up to 20% really of the AP exam is probably just concerned with questions essentially doing these derivative rules in combination. You know, they're very common. They happen all the time inside of other kinds of ideas. But this is something that like we really need to be quite effective at and be able to do these problems like confidently and quickly. And I know you guys aren't quite there yet because it's just starting doing these. But don't feel like you need confidence and quickness exactly right now, because this isn't going away for the rest of first semester. We're still going to be using all this stuff kind of in combination with one another throughout. So like shoot for, you know, like, oh, feeling okay and pretty quick for right now. And like, if you keep practicing and you keep, you know, working at it, like real confidence and real quickness will come. But that's also a part of just like needing reps and practice, and that stuff doesn't go away throughout the rest of the first semester. Okay. And in terms of like layers to a problem, I think the stuff that we did today is probably as much like as many layers to like one of these simple pushing problems as you're going to see, where you got like chain inside of chain inside of chain, and then a product and then a chain. Like that's like the most amount of layering you typically get inside of a problem throughout the entirety of the course. So some of the most like complexity in terms of layering of the problem is happening right now. Like the integral stuff, there's just, with what they're asking you to do, there's not nearly as much layering in the going backwards of it. There's usually only like 2 layers or 3 layers going backwards. There's never like 4 or 5. And there's only so much layering we can go backwards on, because there's some stuff it's not part of the course, and how do you undo this kind of a derivative? And then like the rest of it is really application stuff. You know, like we'll finish the main derivative rules here in the next 2 sections. For the rest of first semester, it's then going to just be applications of things you can do with derivatives. Like, what can I use the derivative to do? What can I use it to find? What kind of problems can I solve with this? That'll be the rest of really first semester, is going to be application driven. And then the same kind of pattern in second semester. You do like about half the semester is learning how to do integrals, and the second half is applications. And I kind of think in a way the integral pieces are easier than the derivative, just because of like the amount of layering, the amount of complexity you can get. Like an easy derivative is easier than an easy integral, but the hard derivative is probably harder than the hard integral that you guys see. Now, in general, that's not true, but for AP Calc AB, that's certainly true. It turns out that some integrals are so difficult, like there's not even a way to do it algebraically. And you end up having to like simulate what the answer would be. Yes?
This is kind of a random question.
Okay.
What's the difference between AB and BC?
BC does more. Is everything in AB plus some more.
Oh, wow.
Yeah, BC just like a lot faster.
Well, some schools do AB and then BC. So if you come in and you've already done all of the AB stuff, it's basically a semester of review of these AB things that you still have to be able to do. And then it's like a semester of kind of new things. But if you're doing BC all in one semester, you couldn't feasibly do it in our school with the number of hour or minutes that I have with you guys. It's just would not be feasible to do. But some places do that, but I think they have a lot more time of class time than we have. You know, we have 8 courses instead of 7. You know, we have 45 minutes of community time every day. There's a lot of like minutes that if you're doing like the same length school day as us with no homeroom and 7 courses, you know, it's probably an extra 30 minutes a week or something, at least, that you'd meet, that I'd have available to meet with you guys. And you potentially could do a BC in 1 year with that, but you'd have to be really good and ready to hustle, like even harder than we're hustling now.
Good afternoon, Notre Dame Prep.
Because some of the extra stuff is quite difficult.
Let's pause for this afternoon for